First of all, welcome to gRPConf India. This is the first time we are doing the conference here in India, and really glad to see the response we've got. So my name is Sreenithi Sridharan. I am a software engineer at Google and an org member of the gRPC team. In this talk, I will cover gRPC's core concepts and its lifecycle. So as Kevin mentioned, if you are new to gRPC, this would be a brush up of basic if you're new to gRPC, you will learn basic concepts of gRPC, and we will also have some hands-on code labs later in the day where you can try out gRPC for yourself. And for those who are familiar with gRPC, this would be a quick refresher of a lot of topics that will help you prepare for the day of more advanced sessions. So let's get started. Cool. So let's start with what is gRPC first. gRPC is open source, high performance, and a remote procedure call framework. It's easy to use, incredibly efficient, and has become the go-to standard in the industry. So in simple terms, think of gRPC as a high-speed delivery service for your data. It quickly and reliably transmits information between your services and applications all over the internet. gRPC is widely used across various platforms, including mobile, web, and desktop applications, and it connects seamlessly with different backend systems. So this makes it an ideal choice for building microservices and distributed applications, whether they are on premises, in the cloud, or within containers. gRPC's popularity stems from its versatility and high performance. So in addition to being available across a wide range of programming languages and architectures, its performance is also industry leading. So the framework features a pluggable architecture, allowing for flexible and efficient integration with various development stacks. Furthermore, gRPC offers a rich feature set for traffic management, security, and also service mesh integration. So a key design choice for gRPC is using protobuf, as it's ideal for to structure service messages. So protobuf's use of binary encoding format results in smaller message sizes and highly efficient parsing. So these benefits contribute directly to gRPC's high performance and high flexibility compared to other RPC networks. Another fundamental design decision of gRPC is that it's built on HTTP2. So this ensures compatibility with many load balancers and proxies. HTTP2's use of binary encoding, header compression, and multiplexing over a single TCP connection makes gRPC a high performance framework that reduces latency and uses resources more efficiently. Now that we've seen about gRPC, let's take a look at some of gRPC's core concepts, and that obviously starts with a channel. A gRPC channel is an object that represents a long-lived connection to a gRPC server identified by a host name and port. So you can think of a channel as a pipe between, through which all the communication between a client and server will flow. While channels are an abstraction concept, sub-channels are what is the real connection to your backend instances. Now, after establishing a channel, you create a client stub from it. So stub is nothing but a layer of generated code. This stub generated from your protobuf definition is that object you will use to make all your remote calls in your applications. So when you invoke a method on the stub, it internally initiates a logical call within the gRPC runtime. This call is then mapped to an HTTP2 stream, which handles HTTP2 stream at the transport layer, which handles the actual data transmission. So before a gRPC channel can connect to the server, there is one more step, or rather two more steps needed. So first step is the name resolution. This is because at the application level, you will just provide a host name to the server you want to connect to, whereas at the transport layer, all we need is an IP address of the server. So to establish this, In gRPC, the name resolution is that process of figuring out the IP address of a server given just from its service name. So you can think of it as gRPC's equivalent of a phone book, where when a client wants to call a server, it will just use that server's name to look up its IP address and establish the connection. Once the name resolver does its part, it returns something called a service config to the next component, which is the load balancer. This service config is nothing but a blob of data that tells the gRPC runtime exactly how to initiate connections and balance requests between them. So the load balancer manages sub-channels, open connections towards the backend services, and distributes the requests among each backend server based on the service config. Finally, things start to be set in motion. So the load balancing code starts up, it establishes the TCP connection to all the backends that are returned by the name resolver. So when RPCs are active, it's the load balancing code's job to monitor the connection status of each subchannel, and if needed, tear down the unhealthy ones. So load balancing essentially divides the gRPC runtime into a control plane and a data plane. A gRPC channel maintains a cached picker which does per RPC routing in the data plane path, while the load balancing code creates and swaps the picker in flight in the control plane. So this ensures that gRPC services can scale effectively and performantly. Once a connection is established, so gRPC serializes this request data using protobuf and sends it in frames according to the HTTP2 protocol. So now that the message has reached the server side mirrors the client side, where server transport receives the request and notifies the application. The server application then just processes that and returns the response that needs to be sent back to the client. So this is one life cycle of a call, starting from the client side, going to the server and back to the client. Now let's look at the 4 types of communication patterns that gRPC supports. First, we have the unary type, which is the classic request response model, where you have a single request from the client and a single response from the server. Second, we have the server streaming, which is the client sends a single request to the server and the server responds with multiple responses. Similarly, we have client-side streaming, where the client sends multiple requests and gets back a single response. And finally, the bi-directional streaming, which is both the client and server can send independent streams to each other. So that was all about a gRPC lifecycle. Now that we've covered it, let's go on to a few more important features of gRPC. The first one is interceptors. So gRPC interceptors are powerful middleware components in the gRPC framework that allow you to intercept and modify gRPC calls before or after they reach their intended destination. So as you can see from this diagram, during an RPC lifecycle, there are certain interception points that gRPC will call to run these interceptor tasks. So interceptors provide a clean way to add cross-cutting concerns, like be it authorization, authentication, error handling. All of these can be done in interceptors, just like without cluttering your main application logic. Next, let's look at deadlines. So in gRPC, a deadline is a client-side mechanism to prevent RPCs from running indefinitely. The client specifies how long it's willing to wait for a response, and if that time is exceeded, the call is cancelled with a deadline exceeded status. This timeout can be set either as like a deadline, which is like a fixed point in time, or a timeout, like a duration, and both are functionally interchangeable. So this deadline exceeded error can occur for various reasons, like a failure to connect to the server, or a server recognizing that the client's deadline is too short to be fulfilled. So one other important feature is that gRPC supports deadline propagation. What I mean is when a server receives a request, it also receives the associated deadline. And now if that server has to make upstream, make more RPCs to upstream services, it automatically forwards that remaining time to those upstream services. So the overall time limit is enforced throughout the system. So now that we've seen deadlines, next also let's take a look at cancellation. So deadlines are a way for automatically cancelling once a timeout has reached, whereas cancellation is a way that gRPC client can manually cancel an RPC that it no longer needs. This cancellation signal propagates through the HTTP2 transport to the server, allowing it to stop processing and clean up resources. For this to be effective, especially for long-lived RPCs, a server handler should periodically check if the call it's been servicing has been cancelled. Upon detecting a cancellation, the server would stop processing immediately to avoid wasting CPU and memory, also clean up any allocated resources, and ideally propagate the cancellation to any downstream services that it may have called. Next, we have retries. So retry is a feature that allows clients to automatically reattempt an RPC if a call fails. So this is a powerful mechanism for building resilient applications that can gracefully handle transient server-side issues or temporary network problems, all without having to put in this complex retry logic within your application code. So when you enable gRPC retry, the client channel is configured with a retry policy. So this policy defines the rules for reattempting the call, like it could be the number of attempts to make, the backoff delay, or even a retriable status code. So when such criteria are met, gRPC will create a new retry stream after an exponential backoff delay. Once the response header is received, no further retries will be attempted, and gRPC hands over the RPC to the application. So another interesting thing is if you have observability enabled in your application, you will see retry metrics, including details like retry attempts and backoff delays for each call. Finally, let's look at termination. So every RPC will eventually terminate, whether it is a successful one or with an error. So the termination of a call is communicated through a status code, which informs the client about the outcome of an RPC. It's important to terminate a gRPC channel properly without it's important to terminate a gRPC channel properly when your application is shutting down. You can initiate a graceful shutdown using the shutdown method, which will reject any new call but allows the in-flight RPCs to finish. For a more immediate stop, we have something like a shutdown now method, which will forcefully cancel all ongoing and new calls. This shutdown method is asynchronous, so you must wait for the process to complete. You can use a method like await termination that blocks until the channel is fully terminated, which ensures a clean exit. So to summarize, we began with the fundamentals, which is like gRPC is a modern high-performance network, high-performance RPC framework built on protobuf and HTTP2. And we walked through the life cycle of an RPC from channel creation, name resolution, and load balancing. Finally, here is a summary of some more advanced features that we looked at. So starting with interceptors, which are powerful middleware to modify gRPC calls before or after they reach their intended destination. And secondly, we saw deadlines and timeouts, which are to prevent RPCs from running indefinitely, and that deadlines will also be propagated to upstream calls, if any. Next, we can also cancel calls if you are no longer interested in the result of an RPC. And a server handler should periodically check if the call has been cancelled before processing the request. Also, propagating the cancellation to any downstream services. Finally, configuring retries for fault tolerance and resilience. And also the best practice is to gracefully terminate all your channels during shutdown. So yeah, with that, we've gone over the fundamentals of gRPC. I hope you all have a good day ahead, and yeah, thank you for listening.